Now, you've had considerable success in designing with your students. You've designed and built and tested a large number of chips, a large number of chips and asynchronous chips. And I don't have time to talk about all of them, but one of them you designed was, you call it SNAP, which is an asynchronous processor for sensor networks, and that showed a huge advantage in power over a synchronous counterpart. And then another is field programmable gate arrays, or FPGAs, programmable logic, where your research led to a startup, Acronix. So can you talk about those two applications and why doing things asynchronously has an advantage over doing things synchronously?
Sure. So I'll talk about the sensor network domain, the SNAP chip that we did. And we sort of looked at this problem. It's kind of funny now to think about it, looking back at sort of late 1990s is when we started looking at this problem. And, sensor networks weren't even a thing back then. But, we had faculty members in ECE at Cornell who were interested in wireless communications, and they could sort of see the writing on the wall that, you could build systems like sensor networks. And so there was a collaboration that came out from that, and that's why we ended up designing this processor. So that was sort of an interesting thing in itself. But what ended up happening was we looked at what people were using in the commercial world in this space at the time. And everybody was essentially trying to take sort of the desktop model and make it small, right? And the problem with that really was that the application domain had some very, very different characteristics. And the first one, which is kind of, it's the obvious one, of course, look, now it's obvious, was that actually these little sensor nodes were doing very little useful work, right? I mean, I have a temperature sensor. I mean, I'm computing sort of the running average of the temperature. I'm getting samples like, every millisecond if I'm really, really aggressive. I mean, temperatures don't change on any time scale that we worry about in electronics, right? We're worried about nanosecond time scales.
Right, and these are very, very, very long.
So, like on my phone, if I look at the temperature, it's like once an hour, right? So, I mean, so that was one thing. There was actually very little work being done. And the problem was that all the conventional systems were being designed in a way that, waking up was a very expensive operation because most of the time you're busy doing useful computation. And so it was okay to have expensive wake up, and then you can do useful work. And so there was all this overhead involved in the full system on that. And so what we ended up designing was this. So in the asynchronous domain, on the other hand, I mean, normally the system is waiting for inputs. And as soon as inputs arrive, you start computing, and then you produce the output, and then we go back to waiting for inputs. And that's sort of a very natural way applications look like in the sensor network domain, right? So there's a very good match between what an application looks like, the sensor domain, and then sort of how we design our circuits. So we said, well, we should be able to design the processor like this and have it be very efficient. And in fact, it was funny, when we first did the comparison, by the time, if I looked at the time it took for inputs to arrive on the I/O pins of the processor to when the processor woke up, did the computation, and went back to sleep, most commercially available microcontrollers you couldn't even start executing yet because you had to wait for everything to power up. So it just shows you that we had a very different design point as a result of that. And sort of the asynchronous circuits made this very, very easy because there's a very direct relationship between the way our circuits worked and what the application domain really needed at the time. So that was that example. And then on the FPGA domain, this was a research project that sort of happened on pretty much in some ways out of sort of an accident, which is that, as you were saying, my group was designing all these chips, and it's a lot of work to design a chip. And what we said was, why don't we just use FPGAs like everybody else does, right? So you don't have to design the chip. You can use an FPGA instead, and maybe it's not as good, but at least you can sort of do a proof of concept design. And when we looked at that problem, it turns out that because of the way FPGAs were designed commercially, they're designed for synchronous logic. So they're very, very good at that. But it turns out that there's a huge mismatch between the resources available there and the asynchronous domain. So the mapping was really terrible. And like you couldn't learn anything about how good your design was by mapping it to an FPGA.
So mapping a design into the programmable component.
Right. So what we decided to do was build our own FPGA, right? That was more suitable for what we were doing. And that's what we did. And then when we realized that actually having it be asynchronous led to a number of interesting speed advantages. And the reason is because the FPGAs were, in fact, even today, FPGAs were slow because it takes the programmability of the FPGA means that the wires are actually much, much worse than you might think because the wires have to be programmable. So there's a lot of circuitry in the way, so it becomes very expensive. And of course, the way you solve this problem in a normal synchronous design is you put pipeline stages and all sorts of things to make the wires faster. But you can't do that because somebody's already given you the design to map to the FPGA. So it's not very easy to add those pipeline stages automatically with software. And in fact, researchers tried to do that and they weren't very successful. Now in the asynchronous domain, it turns out that because the data tells you when it's there, sort of putting pipeline stages is easy. Just do it. Nobody cares because the data will still tell you when it arrives. And so what you can do is you can design an FPGA where all the pipelining is built in. And if the logic is structured in a way that you can exploit the pipelining, then it runs really, really fast. Of course, if your logic isn't, it's not going to run any better. So that's sort of what happened. And so we ended up having FPGAs where we could map, things like DSP operations that ran, in some cases, actually over a gigahertz throughput on an FPGA, which is sort of unheard of.
At the time, that was a very, very high frequency compared to what you could do in the synchronous
yeah.
domain, right? It was
Yeah,
hundreds of megahertz in the synchronous domain.
Right. I talked to somebody who was an expert at a company who was basically hand optimizing their filters, the DSP blocks to run on commercial FPGAs. And I gave a talk at this company, and he came up to me afterwards, and he was very upset because, and I showed him, we could get, gigahertz kind of performance, and he said, he was running at 1/5 that throughput, and he was doing the full design manually, which is an enormous amount of effort.
Optimizing to the nth degree.
Everything, right? It was, it took him 2 years to do this, and here we could do this in 5 minutes by using sort of, and he was very, he was very nice about it, but it was clearly a shock. So that was basically the idea there, that you could actually run a lot faster because of this inherent data-driven nature of asynchronous logic.
So in terms of snap, it was really a power advantage, energy advantage, right? It was more energy efficient. In terms of the FPGA, it was really, there's a speed advantage.
Right, throughput.
The throughput, I should say, throughput.
Yeah, exactly.